the first part is the Lebesgue measure in A. So why we need to, well, why it's useful to go beyond the Riemann integral. So the main, well, there are many reasons essentially, but the two reasons is that, well, we have so better than Riemann integral. So the first reason, you have in general more integrable functions. So the class of functions which can integrate are not just a continuous function or piecewise continuous function. So you can compute the Riemann integral for piecewise continuous function. But actually there is a class which is definitely more general than this. For example, well, essentially it's pointwise limit of a continuous function, which doesn't need to be continuous anymore. And the other problem is that, well, one of the important things is to compute the limits. So when you need to compute, well, what if a function converges, often you want to know that the limit, the integral of the limit converge is equal to the limit of the integral. No? So, and in the Riemann problem, usually the only theorem is the uniform convergence. Okay, so you have a C0 function. Actually, C0 function, the topology is the uniform convergence, so you are sure that it converges to a continuous function. And so you know that if a function converges uniformly, then the integral of the function converges to the integral of the limit. No? Okay? So, but here you have definitely more general properties, or more general passage to limit. Okay, so do I need to explain? Please, because sometimes they say I go too fast or too slow. Please, we have just to tune the speed. So it's okay? I have questions about that? So more general functions. It's not all functions, unfortunately. And more general past the limit, of course, can be any limit. You need to require something. Okay. So let's add the.
Sir,
yeah.
you activated the recording?
Hmm?
The record.
What happened? What the record?
I mean, you.
Ah, I forgot to push this thing. No.
No, it is okay.
It's okay.
Oh, it's okay. Okay. I asked you if you did it.
Yeah. Okay, so let's start. So we need to construct essentially this thing, but the first remark is that the following. So can you give me a particular function? The easy function you can invent. Well, it's not, it cannot be that easy, but the easy thing that you need for sure to give a value.
What?
I'm asking you if, because now the problem is why, in some sense I want to understand why I need to do this thing. And then I'm asking you what is the easiest thing that you can invent that you are sure you need to give a value, which is the length or the Lebesgue measure. Well, I already said the length, so the easiest thing is interval. So let's say I need to measure, let's say, intervals. And then, well, of course, to give measure to intervals is not so well. So I have my tool, I measure thing, but then clearly I want to measure something which is more complicated, no?
Yeah, intersection.
Before.
Yeah.
Intersection of intervals of two intervals is one integral.
Yeah, union.
This is the union.
Yeah.
So, how many union? 2, 3, finally.
Multiply.
But you know, wait a minute. You are cheating because they know already the theory. It's okay for countably. Well, finitely many is okay, no? Because if I want to compute the, let's say, the area of this thing, I need to have this length plus that length plus that length. So finitely many is okay. So it's okay for you countably many. You feel natural, or why I should do that? Well, of course, after you work for years in mathematics, it's natural to take countably many, but there is one reason, because it's the limit operation in some sense, no? So let's say if so you have this interval plus this interval plus this interval, this interval, this joint, and they are countably many. What is the length of the union? Is the limit of the finite sum. Then, okay, I want to measure that guy, so I need, so countably many, then I need to measure countably many. Okay, but then I said length, and it is a little bit switch the integral word to the measure. So what is the relation? It's very elementary. You don't have to think. So what is the relation about length and integral?
The length is an integral of the constant function.
Yeah. So I usually denote with 1 of e. 1 if x is in e. 0 if x is not of e. Then, okay, and now we have to introduce some, let's say, the length, which is not clear, is equal to the integral of the indicator function of e. No? Are you okay with this? Okay, so finally, from the Lebesgue measure, or the Lebesgue integral, which is here, we arrive to the Lebesgue measure. Okay, so if I can integrate in some sense, I can give the measure and then vice versa. Something. Okay. So now let's see. This is just formal. So let's see which properties I want. Everything should be very natural. So the natural properties you want to require, no? So which properties you want to have with this function, which is called length? Yeah. So natural properties. So the length is greater or equal to 0. Let's call it m. Measure of any set is greater or equal to 0.
Translation invariant?
Translation invariant. Okay, let's do some notation. So let's keep this positive. Let me say everything is in the book, in textbook. So here is just if you have question or you don't have time and you want to have another look or whatever, it's really important. And some proofs may be a little bit longer than what I think, but the book is already, well, this is standard stuff since 100 years ago. So. Okay, and finally?
The measure of the empty set is
the measure?
of the empty set.
Yeah, okay, let me say the measure of the empty set, but Yeah, and since I want to have the counter with many additivity, counter be additive, no? So if the measure of the union, let's say for I, EI, and these are disjoint, the sum of the measure of EI. So are there questions here or so this formula, you know, it's correct, no? You know to compute it. And well, okay, but this is a little bit, is not yet. There is still one property in it. And the problem is that if I give 0 to every set, this function satisfies all these assumptions, no?
So the measure of E is different from
Yeah, but still I gave the I don't know, whatever. It's not, there is, because I want the Lebesgue measure.
Measure of the intervals is
The length is the length. So the measure of the, say, an interval which is open or closed doesn't matter. Okay, so this is the point. Okay, it would be very nice if we can prove that this function exists. Unfortunately, this question cannot be decided. In the sense that
how it. I don't understand the remark. What?
this question, if m exists,
Yeah,
cannot be decided.
because it's up to constant multiplying. And, I don't understand.
Cannot be decided in the standard set theory.
Ah, okay.
In that sense. So there are, if you assume the axiom of choice, m does not exist. If you don't assume, you can have a model of the real line where m exists. So this cannot be decided. So so this is the first important thing, the fact. So let's say that a function m, which is defined on the power set of R into 0 plus infinity, and I take plus infinity, okay, let's say it does not exist. I don't want to enter into this logic thing. And so the next question is, well, unfortunately, I need to measure things. So I cannot renounce to the function. So I need to relax some of the stuff which are here. And there is still, and I put something, well, it's a trick. I'm a little bit joking, of course, I'm cheating because I know the answer. There is something in this list together with this one, which I need to relax. I cannot require to hold all these properties. So let's see. So this one, can I have something which is a negative measure, negative length? No. Translation invariant. The translation invariant is like saying that what happened on Earth is different from what happened on Mars. No, you understand? I cannot. Well, I cannot say that the measure of the empty set is not 0. Because then it happens that the measure of every set is infinity. Well, this is the property that I want to have simply because I observed this example. And clearly, if the length of any finite sum is something, and the finite sum converges, the measure of the counter reunion is the limit. Well, and this is something that states what, well, among all functions that there are infinitely many which satisfies the first 4, well, this determines which is your function, no? Because if you start with this one, you can compute the measure for countably many intervals, then, well, you can go on in the construction and give values, length, to count the many different sets. Okay, so we go back to this guy. And what is the property that I said here?
Change the domain. We change the domain.
Yes, power set is too large. So n, so let's say 10. N is defined on a subset of the power set of R. And now we have to define which is the subset. No, because please stop me because I'm trying to be as logical and as of course knowing the answer is easy, but with this, to show you that it's very natural here. Okay, so let's find this subset. This is not important. So which properties should have this family of sets? Okay, so which is closed under sigma union, let's say. Sigma will refer in this theory, the sigma always refer to countable. So countable union.
Complement?
The complement, if I have a measure, the complement should be 1 minus, well, if I have one interval, should be the total measure minus the set, so the complement.
Contain the interval.
Yeah, the two cheating guys, unfortunately. Contains the intervals.
Intersection.
Yes, but the complement plus the sigma is the determinant intersection. The empty set is an intersection, so it's okay. And okay, I should require also this guy. It's not a priori inside, but it turns out that with those properties it's inside. Okay, so this thing is called the Sigma-Algebra. So, just because usually it's presented in a way that you don't understand. But usually it is an algebra because you have the two operations, the intersection and the union. But since we have also the sigma union and then the complement becomes the sigma intersection, it's a sigma algebra of sets. That's why we have this name. Okay, so finally we arrive to the object. Okay, so let me cancel this guy and write the two objects that we have to consider here. Okay. So I'm sorry, I should say about the exercises, the exam. This is let me. Should I wait 10 seconds more, or is
Sì, no, it is.
every year they change. Last year you have to say, I'm starting and waiting. Okay. So the first exercise is the following, and it's very important. Okay. The Sigma-Algebra. So this is essentially important fact. And the measure are, let's say, come together. It is an informal comment. So the example is the following. Define, let's say, the Sigma-Algebra. So let's say the measure, a function measure me from the power set of R into 0 plus infinity as the measure of any set is equal to the cardinality of the set. So it's, let's say, the number of elements is but it's just to say that this is the notation of the cardinality. Okay. Prove that P of R is a Sigma-Algebra and me is a measure. So the name of this measure is the counting measure. Let's see this exercise. P of R, well, I can also say for any set. So P of R is a Sigma-Algebra. Why? It's almost tautological.
It is closed under closure and complement.
You cannot exit the power set of R using set operations, no? Simply because it's made of all subsets. Whatever you do, you are inside this. Okay. So why? So this one is trivial by definition. So let's prove it is a measure. And we had some definition about the measure, which is for the Lebesgue measure, but actually the measure here means that the measure of the empty set is equal to 0, the measure is greater or equal than 0, and the measure of the countable union of disjoint sets is the sum of the measure. So we just change a little bit in the sense that before the definition we had, the properties we required were for a particular measure, which is the Lebesgue measure, which is very important simply because it is the translation invariant measure. But then one can ask for something which is more general. So the which properties I forget about the requirement on the length of intervals, and then just ask the rest of the properties. The measure is positive, is 0 on the empty set, and if I have countable many disjoint set, I require the measure of the union to be the sum. No? If you remember what we wrote, it's I'm just removing the part about the interval. The part about the interval determines the measure. But then you remove that and you say, okay, I can have more general way of, well, I have different instruments, I measure things differently, and I just require this object. Okay, so is it true that the number of elements of the empty set is 0? By definition. So is it true that the number of elements is a positive number? So we are done with this guy. Okay.
Maybe we need to define the sum of infinite.
The sum of what?
Infinite plus infinity?
Well, yes. Oh, yes. We assume that plus infinity plus any finite number is plus infinity. No. Okay. So, you have any doubt how to prove this thing? Okay. So first of all, suppose that one set has infinity number of elements. No problem. Plus infinity here, and this clearly is plus infinity. Suppose now that the union of elements has plus infinity. Well, of course, this should be also one line because it's almost trivial, not by the definition of finite. Okay, so the number of elements of their partition or their set should be plus infinity, no? Because if the sum of elements of each of the I, so let's do this. Let's do this different. So suppose that the set I, the number of sets which are not empty is infinite. So this sum is plus infinity. No? You have a number of sets which has at least one here, and their number is plus infinity. How many elements has the union? Infinite. So it's okay. So finally, the only case is when there are finitely many sets with finitely many elements, and this is just the sum in the natural number. Okay? So question here. So this is another measure. Other examples. The measure of any set is equal to 1 if 0 belongs to the set, 0 if 0 does not belong to the set. Okay, you can verify this is a measure defined on, again, the power set of R. This is called the Dirac delta. On the power set of R.
Is this additive? If we had two sets that contains okay.
Only one. But of course, if I measure the same interval 30 times, I get 30 times the length, but it's not the length of the unit. Okay, so this is another measure. And finally, another remark here, when you put in this example, is that, well, for this particular measure, it also for uncountable union. Just you have to observe that the sum of uncountable many sets is plus infinity if there are more than finitely many sets different, which value is different from 0. Okay, this is a particular example. Very well. So, questions? Is that quite natural, or is out of this world? It may happen. It's out of this world the first time you see this. Okay, so let me repeat the stuff. The stuff is that these are the most important thing you want to preserve. You want to measure intervals, at least for the Lebesgue measure. You want to measure countable union of intervals because it's the natural object, no? And and finally you want to be translation invariant. Then you discover that I'm in trouble. I cannot assign a function with the properties that I want on the whole sets. I need to restrict to some sets, and I discover that, well, the property, see, if I want the countable union, I want to give measure to the complement, essentially I end up with what is called, a Sigma-Algebra for M. So, this domain of my functional which will extend the length. So, in general, I can require, but now what mathematicians do is that they obtain some properties and then they take what is really important and generalize the stuff. Okay, so the fact that I require to contain interval, well, I can forget it. It's certainly because I want to measure intervals, but maybe I don't need to. No, because maybe I want to put some functional, some measure functional on some object which is not the real line. So metric measure space or something, so metric space or some more complicated thing. And then I say, okay, don't matter. I take just the two properties which define the Sigma-Algebra, and then I take the properties which define the measure. So the measure of the empty set is 0, is a positive object, and is a countable additive on the sets. So I obtain these two definitions. So I obtain what is a Sigma-Algebra, forget about that, and I obtain what is a measure on the Sigma-Algebra. And now I do some strange example just to see that I'm not restricting myself to the Lebesgue measure. So, for example, I take the counting measure, the Dirac delta measure, and variations. Okay? So this is the end of the one part. Okay, so now the next point is really to construct the measure. And also here, unfortunately, it's a method that has been refined during the years. So we start with the construction. And now I have to add something here. Because my problem is that I have to find, remember that from the previous definition, I just gave definitions. I'm not exhibiting you either the Sigma-Algebra, which is, okay, you know should contain those objects, but you don't know if it exists or not. But okay, you can use some measure theoretic thing in order to prove that there exists an object like that one. But you don't have when you use some measure theoretic tools, you don't know what you're going to construct. It exists, but you don't know what is made of. And then you need to put a measure. So how to give length what the extension of the length to this measure theoretic objects, you don't know. But we need to have something constructive because I really want to have a method to give the Lebesgue measure to the sets that I'm interested in. It's okay? So this is a constructive method. So what I do is that I relax the sigma-additivity. So I will give a value to every set, which is the extension of the length, but I do not require the sigma-additivity. Sigma subadditivity, and then on the power set of R. So what is called this thing? So what we are going to construct is the Lebesgue outer measure. Now we see also what is outer. So the definition of the Lebesgue outer measure if E is a subset of R, then this is the notation for the outer measure is equal to, okay, this is the infimum of the sum of the measure of the intervals II, such that E is a subset of the union of those intervals. Okay? Okay, let's see some examples. So this is an operative definition. No? Give me a set, take any partition, compute the length of any covering, in intervals, compute the length of this covering, and take the infimum one. It's perfectly constructive. So in theory, you are able to give a value to every set. Okay, so for example, let's say what is the outer measure of the empty set? Yeah, I know, right? You know the theory. It's a big problem. I know that it is boring for you, I'm sorry. You have to do the problem. So it's 0. Yes. Why? I have to prove it.
Interval can be very small.
Okay. So, for example, is the infimum, well, is less or equal than the measure of every interval. It's okay. And the measure of every interval is the length. And so this can be arbitrarily small, no? This can be, for example, minus epsilon, epsilon, and then you get that this thing is 2 epsilon. The measure of a point. 0, again. Is x plus a t.
Any finite set.
Pardon?
Any finite set.
Okay. The measure of a union, a countable union of points. Hmm? 0. Why?
Because the measure is less or equal to the sum.
just like
we,
that.
we take a countable covering with intervals which the theory of the length is.
Yeah, so it's x1 plus, let's say, epsilon.
We are talking about the measure or the outer measure?
The outer.
It's the outer measure. So everything is the outer measure. We don't have yet the measure. Okay, so let's say 2 to the, I cover with the set 2 to the minus I, let's say minus epsilon epsilon. So you know this notation, no, is the length is epsilon, is 2 epsilon 2 to the minus I, no? So what is the sum? So let's say this set clearly is contained in the union of this length. It's okay? And so what is the length? So the sum of the length of these intervals is the sum 2 epsilon 2 to the minus I, and this is 2 epsilon. The outer measure of the irrational number is 0. Prove that the infimum of the sum, the finite sum of length of intervals where the q, the natural number in 0, 1 are contained in this finite sum is equal to 1. Okay. So we know that by the outer measure that I want to say that I use in a heavy way the fact that I take countable union. So this is countable. If I remove a countable, I get immediately some strange thing which says that I'm not going to the correct function, to the correct measure. Okay, this is for you, or you know.
No.
Otherwise, I want, so I leave for you to have fun.
I think there's some problem here. This is equal to the measure of, to the outer measure of Q intersection the interval 0, 1?
This one?
Yes.
No.
This,
No, because I take finite measure, finite covering, not countable covering.
Okay.
Rationals are dense on this interval, so every interval must have to contain every rational, every real number.
Yeah, and then, but also here, wait, what is the difference?
What is?
The difference, even here is the same, no? Okay, but just go on. But it's true, it's because they are dense.
Yeah, no, I mean that when the covering is finite, then if a union of finite intervals contain the rational and 0, 1, then it contains the interval itself. That's it. So always when we take a covering, then the union contains the interval 0, 1.
Sure.
Except of.
Yeah, except of finite.
Okay.
No, but the intervals are assumed to be closed.
Open.
They are semi-open, open as
Open, open.
They're open. Okay. Okay, in that case.
Okay. Just fix it. Let's see what I had. Yeah, nothing. Okay. So let's start playing with this stuff. So the first proposition is that at least M star should agree with the length of intervals. At least. So a remark, because they ask, I forgot about open. For Lebesgue measure, you really don't care about open or close, simply because the length of open and close interval is the same.
Yeah.
For the general case, instead you care. Because this can be a general definition, you replace this M or length of intervals, let's call it length, you replace with some other general function. In that case, the closure or the inner, they differ. The interior or the closure, they differ. So, but here, so M star of the open set is equal to M star of the closed set, semi-open, M star on the other semi-open, M star of the closure. The closure, if it is finite or if it is infinite, okay, just one or two or out of two or just one is that. And it's equal to B minus A. Okay, let me assume this to be finite, no? Let's do for finite sets. For infinite sets is the variation. So we prove only for finite. For infinite set, okay, just variation. We can use a later problem. And then we do something, we prove it for compact sets. Closed or compact set. Okay, so I need to apply the definition. So M star is the infimum of the sum of the length of the intervals, count-remaining intervals, such that is contained in the union of these intervals, open. Okay? So this is the definition, but A and B is compact. So that for every covering, well, what I'm going to say, Chocks are always something missing. For every covering of a compact set, open covering, there is a finite. Now clearly, the sum of the length of any covering is clearly greater or equal than the sum of the length of a subcovering, because I have less elements. Okay, so it just so essentially for compact sets, it's okay to take finitely many coverings, and not for Q, which is not compact. Very well. So let's use the same notation. Denote again with I. Okay. Okay. Now, okay, I have to do that, but let's. I think the book is a little bit long, so I will be a little bit sloppy, but at least. well, you can make the thing form. Let's cancel this guy. So consider the function, let's say, I already used, let's say j of x is the sum of the indicator function of ai evaluated in x for that particular code. And I'm stating that this function, observe that j of x is greater or equal than the indicator function of a. Okay, this is the part that the book takes a little bit longer, but then I want just to switch because it's trivial, no? Do you agree? How many have doubts about this inequality? Or how many believe in this inequality? No one, so it's undecided. Okay, so let's just observe. This is a covering. So every x belongs to one of the sets. Do you agree with that? Okay, so every x here, this function is 1 exactly in that x. You agree? And 0 outside. So one of these elements is 1 in that point. Do you agree? I just say for any point x, there exists an I bar such that it belongs to I bar. So the indicator function, sorry, this is the indicator function of that set is 1, and the indicator function of this one is 1. So certainly 1 is greater or equal than 1. And well, the rest, this is 0 and this is certainly positive. Do you agree? And now, what is the sum of the length of this guy? I'm saying that the sum of the length of EI is equal to the Riemann integral. I just want to use the Riemann integral. Let's say the Riemann of j of x dx. Do you agree? Yeah, because the integral is a linear operation. The integral is monotone. And what is the last? B minus I. Okay, so what I proved? What did they prove? For any covering, the sum of the length is greater or equal than B minus A. Okay, so I deduce is greater or equal than B minus A. Okay, first point. And now I want the other inequality. So I can cancel. So I want to prove that actually is less or equal than B minus A.
B minus 1 over n, B
Yeah.
minus
Take the length of I. Okay. So conclusion. let's prove the other. So to prove the other, so this is the first part. To prove the others, I think I will let as an exercise, or you can do it here. So the points are: observe that if E is contained in F, the outer measure of E is less or equal than the outer measure of F. This is the monotonicity. Are there doubts here? You know how to prove this? Let's do by definition.
Because all the covariance of F is correct.
Exactly. The measure of A, B, let's do for the open, is less or equal than B minus A. You know how to prove that? It's in the blackboard. It's the same. And also if I close here and I close there. So that property is completely general. Take A plus 1 over n, B minus 1 over n.
But what, not y not equal? This is equal.
This one?
Yes.
It's open. I have only closed, and this one is just the same choice as this point.
Okay.
So far I have only this equality. And I use the same test interval to get an inequality. And now I take this one, which is contained in A, B, and use monotonicity. Because from here I get the outer measures, so this is the outer measure. The outer measure of A minus plus 1 over n is is less or equal than the outer measure of the open set. This is less or equal than B minus A because of that guy. And this is equal to, this is equal to B minus A minus 2 over n because of this guy here. Okay, and then and also closed and open whatever you want. Questions? We are just using the definition, nothing else. No questions? No. Well, this is a property for infinite set, no? For infinite set, use the monotonicity. Once you know for finite set that something grows. Okay, so we have this function which agrees with the length on intervals. And star is translation value. So m star of e plus y is equal to 1 star of e. Proof? Everything here is just for the definition, no? definition is
If we take covering of E,
yeah.
then if we translate the intervals of the covering by Y, it's still covering the
Exactly.
same stuff.
And I put is infimum sum, the length of the sum of the intervals where E is contained in the countable union of intervals, open count. Okay, so proof. Translation of covering is a covering of translation. And now a property which was stated, M star is countably subadditive. Which means that M star of a countable union of sets is less or equal than the sum of the countermeasure of all sets. Proof. Everything here is just for the definition. Okay, so let's use the definition. We need to use the definition. No? So, but since it is an infimum, the inequalities like this one are the easy part. The difficult part is always the opposite. You want to have the equality. This one is the easy part. So, how to prove it? But I have to use the definition. So, let's take a covering of EJ. So, let Ij open countable covering of EJ such that the outer measure of, okay, I do the proof with let's say a mistake. Sum over I, the length, ij minus epsilon 2 to the minus j. Then the union over I and j, ij cover is an open countable covering of E. Hence, M star by definition, the sum ij, the length over ij. This is positive, I can rearrange, it's absolutely continuous, sum over j, sum over I, the length ij, and then I use that guy, which is less than the sum over j, the measure, so I'm using now this one. E J plus epsilon. Sorry, this is 2 to the minus j. And then this is less than, so this is equal to sum ij plus epsilon. But in this proof there is a mistake. Even if the argument is basically correct. Now I take a covering. I introduce a mistake to make the lesson less boring.
Maybe we should suppose that m star of Ej is not infinity.
Yeah. Yes. And if it is infinite,
It is done.
it's obvious. Okay? So the error is that. Otherwise, trivial. Okay, so let's do some exercise and then I think we conclude for today. Are there questions here? So today what we reach is just what we constructed is a functional explicitly constructed. This is explicit. Well, it's explicit in the same way you can compute limits. It is explicit and it gives a value to every set. It has all the good properties. The length of intervals coincide with my functional. It's translation invariant, but that is not countably additive. It's subadditive. So the next step is to define the sets for which will be countably additive. Okay, because it has all the good properties. The measure of the empty set is 0, whatever you want, but this guy. And now the domain of the measure is the set for which the equality holds whenever they are disjoint. So this is the next step. So today, now we end with some exercises to warm up. The cardinality of 0, 1 is okay, now it depends on your notation. Let's say is greater than okay. Well, this is not correct. Should be Aleph 0, no? Depends on your notation. This means the countable number, the cardinality of the countable number. Proof?
Because the measure of the interval is 1.
Okay. Oh, okay. There are whatever you want.
The counter argument. The counter argument of explaining.
Yes, I clearly want to use what is written here. Otherwise, yes. Okay.
Yeah, as I said, if it's countable, then we'll count
Its
it.
measure is 0.
Its measure is 0.
Yeah.
Why?
Because proved,
You have to use all those properties. You cannot use what we had before. You remember that we proved that whatever
Measure
is.
of countable system zero.
Ah.
Improved.
We prove. Perhaps was an exercise. Yes. Yes. Okay. Yeah. Otherwise, because the measure of 0, 1 is equal to 1, and the measure of let's say a countable set is equal to 0. the outer measure of the irrational numbers. How? What do you think?
One.
It's 1.
Because we know that the outer measure of any countable set is 0.
And then?
The additive property. Oh, we don't have an additive property, we just have a scalar. So, okay, this proves one direction, one inequality.
You can take covering.
You have to apply it in the code.
For every rational number, there is an interval that contains a point. And,
You take any covering
and it's to cover
and then then you have something. We don't have many instruments here. No, we can also only use the cover. Okay, define A to be a G delta set if A is the intersection, a countable intersection of an open set. Then, for all sets E, there exists a, so let's say this is in the power set of R, a G delta, such that the outer measure of E is equal to the outer measure of A. So essentially, this property C tells you that what you are measuring are G countable intersection of open sets. Indeed, at the end, what will be constructed is, well, you have countable intersection of open set or countable union of compact sets, and the rest is just you add set of measure 0, which is not.
A containing E, right?
Yeah. So you're right. Otherwise, it's well, that statement is correct because I can also, without this one, this is a stricter requirement. But then it's the important part. So which will be this A?
We take the open covering and take the union. It's A
And the intersection, taking the infimum is, since we are in R, the infimum is reached by sequences. And so it's a countable intersection of the countable union of the coverings. Okay. We still have 5 minutes, but the next, look, there is some nice exercise here. Let's go on. This I can cancel. If the outer measure of A is equal to 0, then, what I want to say, then for all B, the outer measure of, what to take the union, A of B. So sets whose outer measure is 0, they do not play any role when computing the pair. is as usual. You take, so far we have only the definition. You take the covering. So this is a measure, you take a small covering, another covering of this guy, the union is a covering which is the covering of this guy plus something very small, arbitrary small. Okay, can you deduce from this guy this exercise here? Yeah, now it's easy. Another thing is very important, and this is a way of constructing measures which we do not use now. Because, okay, it seems a little bit, this is more, I prefer this book because it's really more direct. It was more direct, it's more natural. You build in because you need them. No, it's not just to start with a definition and then, but suppose that A and B are such that the distance of AB is greater than 0. The distance is, you know what is the distance of two sets? Take 2 points, one in one set, one in the other, take the infimum. So are the two closest, or well, if they are closer, they're closest. Otherwise, they are the limit or whatever. Then, the outer measure of A union B is the outer measure of A plus the outer measure of B. Yeah. Now I know, but it's the definition. It's again only the definition. So you have to find two partitions, sorry, two coverings, and prove that because of this property, essentially you have, well, you have to touch a little bit, you have some cover which is even better, and they are disjoint. You see, since they have positive distance, you can find coverings which are disjoint. They do not overtake each other. And then for coverings, the sum is varied, and then you pass to them. Okay, so this is the end of the story. And now it's which one? 8.